Okay, this would be lecture number 16 for the day scheduled to be on May 28th. This will be the last two sections of Chapter 9, the last half of Chapter 9. More about hypothesis testing. This time we'll be using the t-distribution because we don't know what sigma is. All we have is s, coming only from a sample. And then we'll have proportions. Just about always here we'll be using z. And sometimes it's a good idea to check and see if NP is greater than 5 and NQ is greater than 5. So we'll do that kind of stuff as well. And let's see, let's go over to the other one. Okay, so here we are with hypothesis testing for the mean with sigma unknown. I'd like to change colors, so let me see if I can do that. Okay, all right, so let's move on. All right, so objectives here. Find critical values in a t-distribution. This will be a bit of a review, but it doesn't hurt. We don't see it as much as z. Use the t-test to test a mean when sigma is not known. In other words, we do know s. S is known. And, well, we're barely going to do this. For some of you who really like p-values and have technology, you can take a brief review here and use p-values, even for the t-distribution. But for most of you, don't worry about it. That's not going to be anything we pursue. In fact, there's no requirement for you to do p-values in this class. It's not a bad idea to know about, but do you really have to? Not necessarily. Okay, so finding critical values in a t-distribution. First of all, identify the level of significance. That would be alpha. Identify the degrees of freedom. Very simple formula. No, you don't have to show your work. Not on this one. Just take n, subtract 1. And if you don't find it on a table, just pick the closest one. Or if it's really large, like in the hundreds, just go ahead and use the z value found at the bottom of the page. We're going to give you a different table that you can use, which I think is easier to understand. We'll talk about that in a minute. Find the critical values using a table, whatever table it may be, maybe not particularly that one. And, of course, n minus 1 degrees of freedom. We rarely, in fact, I don't ever plan to give you degrees of freedom. I plan to let you subtract 1. And so if it's a left tail test, we have one tail with alpha. There's a certain column for that. You won't find it in your book. We'll be giving it to you. We have shown it in one of the slides, though, if you want to look that over, the first time we talked about the t-test. So if it's left tail, simply you stick a minus sign on, negative sign. If it's a right tail, it's the easiest of all because you just leave it alone. That's the easiest plan. And then if it's two-tailed, then you simply have to go to the two-tailed header. You don't have to divide anything by 2 if you don't want to. Just use the easy table and be done with it. Unless, of course, you're using a graphing calculator. Then you get a slightly better value for your experience here. So anyway, those are the pictures. We've seen them before. And we'd like to find, for this example, find the critical value, and they like to call it t sub 0, which is nice. Keeps it separated from the other t values. And here, alpha, the standard 0.05, which we see so often, n is 21. And we'd like to just find out what it is. So this is just a review. If you don't really need the review, I suppose you could skip ahead or just stay tuned. We will not be taking that long with this review. Degrees of freedom, it's very, very simple. Just get 20 out of that. Use a table, whatever table number it is. Look at alpha 0.05 in the one-tail alpha column. And it is left tail, so yes, you will be putting a minus sign on. The table never does that for you. It assumes you can do that yourself. So t here will equal negative, as my pen just shut off, let's get a different pen, will equal negative 1.725. There's a minus sign there. And there's a better picture. This is what it looks like. Minus 1.725 is a value that's getting pretty far over. T's are comparable to Z's, except it usually takes a little bit of a stronger T for it to get into the corners or tails, so to speak, to kind of overturn HO and finally pick H1, the competing alternative hypothesis. The further you are away from the center, the more likely you are to be in the alternative hypothesis, which is so often what the object of statistics is. At least that's what I saw in my jobs as a statistician. Anyway, looking For another example, let's find another critical value t. For a right tail test, that's the easy one. Alpha is 0.01, n is 17. So let's take a look. Degrees of freedom, very simple, 16 of course. And we'll go to the table, whichever table it may be. Look at alpha equaling 0.01, one tail alpha column, but yes, we will have a positive value, so you just leave it alone. That's the best. So here we're rooting for right tail test, whereas Z we were looking for left tail test as being the easy one. So please notice the difference. And t will equal a positive 2.583. T stands out. It's got 3 decimals every time. And even if there are zeros in the back, t gets 3 decimals. So many students don't pay any attention to that. And that's because when it comes to probability, I'm pretty open-minded. But when it comes to Z's and T's, you really should follow the rules. And certainly in tiebreakers, I really do enforce them. Depending how well you're doing, sometimes I don't bother if you give me too many decimals for Z and still find the right answer up the table because you rounded in your head really fast. I guess I'll accept it, but so many people don't. They just get the table wrong or screw up in the calculator. That's why I say what I say. Plus, these are the standards that are used. So t point equals 2.583. That's getting pretty far over, but notice we're not really comparing it to anything yet. We're just simply looking up values of t right now. This will be the last example. So now we've got a two-tail test. Alpha is 0.10 and n is 26. So the degrees of freedom, of course, is 25. Very, very simple. Just subtract the ones. And then look at alpha equals 0.10 at the two-tail alpha column. Key difference will be the two-tail column. It's really two different values. The positive one you get directly and you stick a minus sign on, or if you prefer, just say plus and minus. And these little notes on the side are just kind of reiterating what the alpha is, level of significance. So here we have a negative version, here we have a plus version. And I just say plus and minus and be done with it, but some books are more formal than others. And yeah, I kind of walked over it there, but there are our t values. Almost like carving out a confidence interval in a way, but not so much exactly that. It's just got some similarities when you have a two-tail test only, of course. Now we have another point of view here. The t-test for a mean is a statistical test for a population mean, and the test statistic is the sample mean x bar. And yes, we're going to take x bar minus mu divided by s over square root of n. If that was a sigma, this would be z. That's all there is to it. S goes with t, and sigma goes with z. Once you see that pattern, it makes your life easier as far as this class is concerned, at least. I can't guarantee you about anything else in particular, but anyway, you have to have a random sample. Yeah, it can't be like completely cherry-picked or something. That would be like a convenience sample, typically unreliable. At least one of the following is true, and I like the way this experience is much quicker than our very formal book. It's either normal or greater than or equal to 30. And there were a couple people who had Weber questions even today, and they thought n equals 30 wasn't going to make it, but it does. Most books will say n greater than or equal to 30 does make it normal. By the way, normal is z or t. So yes, normal doesn't always mean z. It means you've got z or t. T is your backup plan, plan B or plan T, I guess you could say, because you don't have the sigma. So you don't have everything going for you, but you've got enough going for you that you can still use what they call normality. Both the curves look normal. They look bell-shaped. They're just a little bit different shape. But, of course, degrees of freedom, like always, is n minus 1. So here's kind of a checklist that you can follow if you want to. Oh, yeah, verify that sigma, is not known. The sample is random, and it's either normal or n greater than 30. If you have both, that's just a bonus. Let's go to plan number 2, or part number 2. State the claim mathematically. In other words, state HO and HA, also known as H1, and you may use either one, it does not matter. And verbally, identify the null and alternative hypotheses. So you're going to have either mu or you're going to have p. Those are the only two parameters we discuss, and you're going to have the equal sign upstairs in HO, and down below in H1, you're going to have either greater than, lesser than, or not equal to. That's it in a nutshell. So not a big deal. Anyway, alpha will be given to you. We're not going to worry about that. Identify the degrees of freedom. Of course, n minus 1 is your degrees of freedom. Determine the critical values. Use whatever table you have. Determine the rejection regions. Notice with the t-test, that's how we're going to do it. We're going to almost completely avoid p-values unless you're using technology. Then they work just like before. But for most of you out there, I'm afraid we're not going to use p-values. This is just easier. We brought in this critical value method with z, and as I've said, and I'll keep saying it, there's no obligation for you to ever do p-values in my class, except perhaps in web work or the occasional written problem that happens to ask for one. But on a test or a quiz, no, you don't need it. But you can use it if you want to. So anyway, t is, as we said, x minus mu divided by s over square root of n. And we make a decision. So it's up to you. You're the umpire. You're the referee. Do you reject HO, which means you like H1 kind of, or do you fail to reject HO, which means you basically like HO? So if it's in the rejection region and in the tails, the dark zone, yeah, you reject HO. And otherwise, you don't reject HO. They like to put it in terms of HO. That's just the way they like to do it. Now, if you like to say what you prefer and you show your work, I will certainly accept that for full credit, because I'm not quite that formal. Okay, interpret the decision. So yes, we can always ask you to comment. So you should expect that we'll ask you to comment for some points involved in this. It is a process, and we'll have a few of them on the final. So here's an example, hypothesis testing using the rejection region, which is all we're going to be using today, including 9.4. So this is the way to get used to, I would say, unless you've already figured out your graphing calculator. Okay, used car dealer says the mean price of used cars sold recently, don't care about that number so much, is at least $21,000, dollars, but you suspect this claim is incorrect. You find a random sample of only 14 used cars sold recently in the last 12 months has a mean price of only $19,189. Oh yeah, there's a standard deviation there. And they had a sample. Notice this is all in one sentence. This is how to read math and read statistics especially. You've got your X bar, that's from the sample, and your standard deviation. How could that be sigma? That doesn't make any sense to make it sigma. Of course that's S. It's obtained from our sample of 14. But then even 14 is suspicious. Bah, here it is, normal. So we're good. We don't need 30. We have the word normal staring right at us. Even approximately normal is good enough. But if they don't say anything, or if they say words to the contrary, then of course we would not be doing those types of problems in this class. And the alpha, by the way, was 0.05. I didn't actually stop and notice that, but that's kind of the standard that usually occurs. Okay, sigma is unknown, so we do have S, and we will be using the t-distribution as we continue to do in 9.3. The claim that the mean price is at least $21,000. Well, that means that we'd be looking at least, and here's a case where you could put greater than or equal to if you want to, so I'll put it off to the side, but I'm still trying to get people to follow the easy system of just using equals. However, though, the opposite of the claim will be less than 21,000. And notice that 19K that they had, approximately 19K, that's headed in the direction. And that's a hallmark of virtually every problem. So for a one-tailed test, you're not sure which way to put the arrow, look at the sample stat. We usually don't go the other way. We're not going to give you a $50,000 average, which wouldn't even be worth testing. I've seen them. They do happen. But basically, there's nothing to test. So we don't usually waste our time with that. Okay, test is a left tail test. The level of significance is the standard 0.05. DF, of course, is 13. Okay, so using a table, the critical value happens to be, for a left tail test, negative 1.771. So they assume that you can look that up or find it on your calculator. And the rejection region will be those that are less than that number. No point in putting an equal sign in, because this is a continuous number and it will never be exactly equal to a number that could be taken out to many more decimals if you so desired with a calculator. So T is the standard number. If we don't have it handed to us, which we almost never do, then we do have to calculate that. And we do see that the S, not sigma, is the mu, let's make that mu, is equal to $21,000. And T does work out to be a negative value because it's a left tail test. And that looks fairly extreme. Now, I'm not sure because this isn't Z. It takes a little bit more of a push for T to get out there, but let's just see what happens. Here's the picture that I think says 1,000 words, and I'm really hoping that most of you will give me a picture on the final. perhaps even on quizzes, but that's a little harder with the Blackboard style we have. So anyway, the point is we have two different t's to compare. This is the one that we obtained from the algebra. Let's go back and take a look. Yes, we actually looked this up in the table. I said that wrong. So that's the table value, t0. That's the line in the sand that we have to beat. And then as we calc the t, we have a value that is more extreme. And you can see quite visibly it's landed in the rejection region. So you'll reject HO. But if you happen to prefer HA or H1, I will take that for full credit as well. Just don't say accept. Accept is kind of too strong a word, and then you're really kind of asking me not to give you full credit if you say it that strongly. Okay, there is enough evidence at the 5% level of significance to reject the claim that the mean price of used cars recently sold is at least $2,100. Yeah, it's not. It's definitely less than that, and that's where H1 was headed. In fact, it's almost as simple as saying this is H1's territory and there's HO's territory. Notice it could go as far over to the right and we wouldn't care. Because at some point it gets to be just far enough to the left, and the T's are comparable, that we've crossed over onto the dark side, and that's where H1 lives, and we do like H1, and we'll reject HO. That's how it works. That's how it works. So is that 19,000 something strong enough? Yes, it was. Okay, and here's another one. An industrial company claims the mean pH level of the water at a nearby river is 6.8. We selected 39 water samples. Yep, that's more than 30. Don't need to see the word normal necessarily. But we measured the pH of each of these, and the sample mean and sample standard deviation are 6.7 and 0.35. And it's all in the same sentence. They did not say this came from history or some other situation. So that is definitely S. So you just have to practice enough of these to see the pattern, because on a test, they're not going to be laid out for you like they are here. So I think that's kind of obvious. You've all been in classes before, in math classes, and yeah, you just have to kind of figure it out. And most of you will. And even then, if you don't figure it out perfectly and still show your work, you're still getting some credit for it. Is there enough evidence to reject this claim at 0.05 for alpha? And notice there's no direction given. I'm looking, and I don't see a greater. I don't see a lesser. Don't put it in unless you can see it. Maybe even circle it. So, because, sigma is unknown, and we do have a greater than 30 scenario, we can use the t-test. And the claim is the mean pH level is 6.8. So mu equals 6.8, and then there's nothing else to do. And you call it H1 or HA, we don't care. But mu would not be equal to 6.8. So something somewhat bigger, maybe like an 8.0, or something quite a bit smaller, like a 6.0, would be clearly in H1's territory. But how far in can you go and still get H1 to come out as your favorite hypothesis? Or another way to say it, what's like a confidence interval for HO? This is like an inside-out confidence interval, because it's another two-tailed test. Just another way to look at it. There's no obligation for you to look that up. Alpha 0.05 for a two-tailed test, degrees of freedom are 39 minus 1, which is 38, probably on your table. If the table doesn't have it, go to 40, because that would be the closest one. So using a table, critical values happen to be plus and minus 2.04. You can check that yourself. The rejection regions then would be for t to be less than the negative value and greater than the positive value, the tails. That's where you reject. Out in the dark zone, the tails of the test. The standardized test statistic is t equals x minus mu, and that's divided by the standard error, s over square root of n, and we assume, of course, that mu is 6.8, and t then, because we are subtracting and going towards, well, in this particular case, our value we found is 6.7, and the mean was 6.8, so that's going to be a negative. We're not showing you all the details. We figure you can double check this if you want to, as long as you're able to do it later on. That's a negative value, but is that far enough over? I don't know. Let's find out. And this book does actually show you better pictures, I think, in a lot of cases. And so when we look at the rejection regions, we find that they are plus and minus 2.024, because we have 38 degrees of freedom, and we also have the two-tailed, at 0.05. So there's lots of notation you could use, but the point is you do get plus and minus 2.024. It's not far enough over. It's close, but we're still where HO lives. HO grabbed big hunk of the territory, 95% of the land, so to speak. And yeah, not too surprising that we're going to get a value in the confidence zone, I guess you could say. But we're not rejecting HO. We prefer HO. So I'll just go ahead and say prefer. Be a little bit more direct about it than most statisticians like to be. Okay, here's another one. This one has p-value. This one is the only one today that we'll use with p-values, and this is for those of you using especially a TI 83, 84, 89. And we didn't get you the first slide on this. Let's just quickly summarize this. Sigma is unknown, sample is random, population is normal. We're using the t-distribution, and the claim is a mean wait time for some kind of a wait is less than 14 minutes. So, okay, we will have a null and alternative hypothesis, and that's the claim to be less than, so mu would be less than 14, and then just by default, let's just say mu is equal to 14. Of course, we'll give you credit for greater than or equal to, so I'll give credence to that, even though you're thinking too hard sometimes if you say it that way. Plus, I will have my problems a little bit more clearly read than occasionally the book may go for. Try to give you slightly easier problems, but this anyway for some of you is for the TI-84 plus, and here are some of the directions that you should give me. Otherwise, I assume you're using a table. Unless you specifically tell me you're using a calculator, I assume you're using a table. Now, if I get a different value than you, I'm wondering what the heck's going on here, because you forgot to tell me what you were doing, and then points can easily come off your tests. So please be consistent about it. If you're a calculator user, start using calculator steps, because without the calculator steps, that's just not fair. I don't know what you're doing, and frankly, you're not going to fill me in. Well, anyway, I won't go there. But meanwhile, we do have all the things that had to be typed in. You got your mu, you got your x bar, and all these things that perhaps we didn't read all the way, but we're just kind of doing a quick review of the calculator. And oh, by the way, it happens to give you a p-value. That's a pretty large one. About 19%. That's not particularly rare. We have a 19% p-value, so that's not rare at all. HO loves that, so we do pick HO, but it would probably have a prompt for you to choose which of the ones to go for, and this was a left tail test as I remember, yes, so we would have to pick the less than choice and just go ahead and say that. And then we have a t-statistic. Typically we'd stop this at 0.904. For 3 decimals, they give you more, and on and on and on. And most of you are not really using this, but that is just what some people can do. Just tell me. So P is a very large 19%, and it's way greater than the given, which we're now finally giving you, alpha 0.010. So you fail to reject the null hypothesis, so we do prefer HO in this particular quick example. Not enough evidence at the 10% level of significance to support a claim that the mean wait time is less than 14 minutes. So what we got, I guess it was 13 for X bar. Not enough. That's just a tiny bit less. That's just not significant. Okay, back to our book, and you can refer to the book example if you wish. A psychologist claims that the mean age at which children start walking is 12 and a half months. And so she wants to check on this. She takes a random sample of only 18 children and found the mean age at which these children start walking is 12.9 months. That doesn't sound like very much. That's just a few days. And standard deviation, it's pretty tight, but I guess it's not super tight. But now we're down to only a 1% significance level. That's alpha 0.01, by the way. And can you conclude the mean age at which all children start walking is different? Big word. It changes the game from 12.5 months. And of course, because we only had 18, we did need to see this word normal, so we're good to go. They wouldn't send us into oblivion. Not now. Okay, so we have these setups where the mean was either equal to 12.5 or the mean was not equal to 12.5. And we do not know, and this is an error, do not know sigma, so we're using the t-distribution. And we do have normal, despite the fact that n happened to be small, we got saved by the normal distribution, saved by the bell, you could say, I guess. Okay, so we do have that going on. And now we can take a look, and this is assuming that you don't have the nicer table, so I guess bear with me for a minute. Alpha 0.01, the not equal to sign means, of course, it's a two-tailed test. You can miss it either on the high or the low side. And so the area in each tail, if you just felt like calculating that out, would be 0.005. And if you're using the older table for some reason, which I guess you have the right to do, you'd have to do this extra calculation. So I'm kind of hoping you don't, but I can't make you. If you just got into this, well, okay, whatever. So anyways, we look up the values from whichever table. We do find plus and minus pretty strong values, minus 2.898 and plus 2.898. Can we beat that number? It doesn't sound like it to me. We're only off by 0.4 of a month. Okay, so here's the picture. A picture's worth 1,000 words. Love them. And 0.5% in each tail, and T has to slide over pretty far to get those outer 0.5% in either direction. Now, here's the bottom line. For most, well, if you're using a calculator, you would actually have to do this calculation on its own. You get a standard deviation of about 0.189 or so. You should put about 4, maybe 5 decimals. 8, yeah, that's even better, I guess. But now the t that we're really looking for is the difference of 0.4, divided by the 0.18856, whatever. And so here it is, a kind of a moderate positive 2.121. Let's go back quickly to the picture where we landed, and they should have put this in. It was 2.121. We are in the do not reject HO portion of the table, or of the curve, that is, and so we know what we have to do. We're going to prefer HO. We're not going to reject it. You may say it either way. You don't have to say both, but it falls between. The 2.121 falls between the two critical points, non-rejection region, fail to reject HO. So we can state the difference between the hypothesis population mean and the sample mean is so small that it may have occurred because of sampling error. However, notice that T was kind of large, so maybe it wasn't all that small. Maybe we were just looking for a very strict bar to cross, and we didn't quite do it. Valiant effort, maybe. The 0.4 actually covered more ground than I thought it would be, but it didn't quite make the extreme values that we had to overcome to cross the line in the sand to finally reject HO. See, I guess I had it easy because virtually all the time we were trying to fight HO, fight the power, I guess you could say. But we were almost always trying to overturn the null hypothesis. So we were just about always rooting for H1. But you guys won't be doing that probably. You're not sure what to do. So I'm just telling you how I root against these things. Here's another example. Management at a certain bank is always concerned about the quality of service provided to its customers. Oh, that's the bank that does that. Oh, that's good to know. But Massachusetts is a long ways from here. Well, anyway, I'm sure there are a lot of good banks out there. With the old computer system, a teller at this bank could serve an average of 22 customers per hour. But the management noticed that with this service rate, the waiting time for customers was too long. Recently, the management of the bank installed a new computer system in the bank, expecting it would increase the service rate and make the customers happier by reducing the wait time. An inverse relationship, going a little faster, get through the line faster, maybe even keep the social distancing, which you're supposed to do. So, to check to see if the new computer system is more effective than the old system, the management of the bank took a random sample of 70, and these hours are each random samples, by the way. That's an interesting thing that you probably hadn't thought of. They found that during these hours, randomly selected hours are not cherry-picked to be like Friday at 4 o'clock or something when everybody's getting off work. Found that during these hours, the mean number of customers served by tellers was 27 per hour, standard deviation of 2.5. But, once again, a strict alpha, 1%. Can you conclude that the new computer system is more efficient than the old computer system, which means it speeds things up? And 27 is bigger than 22. Question is it big enough to matter? Or is it just due to random sampling error? Well, that's the big question. Of course it's bigger, but is it enough to make a difference? Okay, so here we have mu equals 22 versus mu greater than 22. And yes, sigma is not known. Sample size is large. And so we didn't have to worry about normality, and so we're using the t-distribution, no surprise. Significance level, the type 0.01, but it is a one-tail test now. It's a right-tail scenario. The alpha is 0.01, so of course, subtract. And many tables would not give you 69 degrees of freedom. Your book happens to have a slight advantage here by offering that. But if you had to call it 70 because you don't have the technology, that's never a problem. Just pick the closest one. Critical value for t is 69, and of course then we look up that value, and right tail says just leave it alone. But that's a pretty strong number, 2.382. Can we beat it is the big question. And we're not comparing p-values here, we're just comparing t-values. Like we can compare z-values if you want. Okay, here's the picture. So the question is, are we over here or are we over here? That's the big question right now. So our t will be able to tell us this. Or if you've done this on your calculator and you don't happen to look at t, although I could always ask you what t is, you can just give me the p-value and compare it versus alpha and do exactly the same kind of a thing. P-value does provide a little bit more information. Okay, so to find the standard error, s over square root of n is about 0.30, but 0.2988. That's what I would use. And so t, x bar minus mu, does give us a difference of 5. You can see the 5 in the numerator. But as we divide by a small standard error, look at that t-value. It's huge. So yeah, we're way over there. So let's cross this out, cross out that. Yeah, this is where we landed at about 16. So yeah, I think we're going to reject HO, and strongly at that. I like to put little comments in when it's an obvious call, or even if it's a close call. I like to just add to it. I know some statisticians are offended by that kind of thing because they're very uptight perhaps, but if you'd like to strongly reject HO and it looks like you have reason to do that, go ahead, fine with me. Okay, anyway, it's way bigger than 2.382, not even close. So this is just not a close call at all. The p-value would also be very low, and you could see it that way as well. But anyway, we definitely reject HO. I would strongly reject HO myself, or strongly prefer H1. That's another way to do it. So, looking at what the hypotheses say, which really helps your comments, we conclude that the value of the sample mean is too large compared to the hypothesis value of the mean, and the difference between the two is not to chance alone. In fact, we're going to hedge our bets and say may not be attributed to chance alone. So yeah, something's really going on here. It does look more efficient. More people per hour, less waiting time that go together like this. So yeah, the efficiency is nice. Okay, this is particular to your book. I don't plan to give you that table, but you could go all the way to the bottom, and the same goes with any t table, the row of infinity, and that happens to be z. T becomes z in a limiting kind of a way. As n goes to infinity, t is just the same as z. It's when the n values are smaller is when the t really pulls away from the z more and more and more. So we use the normal distribution if that were to happen. Of course, calculator will give you all kinds of good information, even for values in the thousands. Then you can see a minor difference between the two if you really looked for that. Okay, we're over to 9.4 now, so this is the second half of today's lecture. We're going to go to the proportion, and z is in control. We'll take p hat minus p, and according to this book's notation, sigma sub p is the standard error, where sigma sub p is equal to root pq over n. I prefer personally to just bundle it together. If you're not using technology, I do have to recommend this. Just put it all together. I mean, why stretch it out? But I'll let you choose. This whole pq divided by n can go down there and you can figure it out. You can figure it out separately and all that. And q, of course, we already know is 1 minus p. Okay, so let's take a look at an example. Refer to what you could find in your book, 9.9, and I have a follow-up example, 9.11. So according to a Gallup poll from about 6 years ago, 20% of traditional college grads, these are traditional college grads who earned their degree before age 25. I guess I was 26. So I'm not a traditional college grad. So a lot of people I know weren't because of various reasons, but that's no big deal either way. They were emotionally attached to their alma mater. I'm not sure how you measure that. So some people don't even care where they graduate from, and some have an emotional attachment, especially if you live in the area. then I suppose you have even a more attachment. It depends. Well, anyway, suppose this is true for the entire population of traditional college grads, and so we take a huge sample, 2,000 of these people who graduated kind of early, I guess, and they could say that 22% said they're emotionally attached. That doesn't sound like much. I'm a little surprised by that, but well, whatever. Using a 5% significance level, there's your alpha 0.05, the standard one. Can you conclude that the current percentage of traditional college grads who are emotionally attached is different from 20%? So 20 is, of course, different, but is it really different or around the same, about the same value? It's only off by 2%. So that's one thing. But notice that sample, 2,000. Wow, yeah, that kind of makes your 2% look a little bit more significant, but I'm still not really sure. A lot of the time I make guesses on these things, and I'm just not sure. So the idea is just to figure it out. Okay, so we have either P equals 20% or not equals 20%. It's a two-tail test. And yes, we always like it a lot when you show that you can use this. Let's correct the error. NP will equal 2,000 times 20, which is 400. Of course, that's greater than 5. And yeah, if NP is 400, then NQ better be a lot bigger. It's 1,600. That's way bigger than 5. And so, yep, normal distribution is good to go. And we always like it when you remember to do this. To me, it's like a little bit of extra credit, unless, of course, we specifically ask you to do it. Then you don't have a choice. But sometimes we just want to move on and get to the question, and I'm not going to give you any stumpers that you can't do. Not on test anyway. So anyway, the not equal to sign, of course, says it's a two-tail test, and we have the significance level of the typical 0.05. And yes, if you're using an older table, well, actually, this is for the Z now, so we probably should do this anyway. Yeah, so with T, you get kind of a shortcut using the newer tables. With Z, you don't really get that, except sometimes you do see familiar Z's, like this one. The alpha over 2 is 0.05 over 2, which means there's 0.025 in each tail. And this one does have, as we've advertised before, the most popular set of numbers in the entire class, plus and minus 1.96, because this is an awful lot like a 95% CI. So instead of concentrating on what's on the inside, we concentrate on what's on the outside. On the outside of both tails is 5%. Notice 5% plus 95% is 100. Yeah, they're complements, all right. And so that's why those Z's are exactly the same. And the advantage of Z is you start to see the same ones over and over again. Although we do have the complication of 1- and 2-tailed tests, and sometimes they throw in 97%ers, but I've already assured you we'll only do 90, 95, and 99, although we could have 1- or 2-tailed tests, so you should be pretty good at that. So anyway, this is where we put the lines in the sand, the critical values of Z, where we change our minds as we go from left to right. At first, we like HA, or H1. In the middle, we like HO, and on the far right, we like H1. So that's our decision-making preferences, if you wish. And then P, if you want to do a P scale, which they haven't really done, P is 0.33 right in the center there, I guess. Okay, so let's calculate some stuff. Sigma sub P hat. PQ over N, if you're doing this separately, which you have every right to do, I don't find it particularly necessary. And certainly more decimals doesn't hurt. If you're putting 4 or 5, you're probably okay, but 8 is always better. 8 is enough, I guess. So Z is equal to P hat minus P divided by that sigma. So you got your 2% on top, 0.02, divided by the standard error, which is less than 1%, which means our Z is a 2.24, I'm sorry. Now let's go back and take a look at what happened. Let's see, I gotta go back here, and 2.24 is over here. I'm surprised they didn't put that on the graph, but yeah, we're in the far right tail. We're gonna prefer H1, or more formally, reject HO. They will say that coming up right here. So yes, it falls in the rejection region. It's just too far over. It's crossed over to the dark side. We reject HO or prefer H1 and conclude the current percentage of traditional college graduates who are attached to their alma mater is different, not greater. It's a two-tail game. We can't change it to a one-tail game. You have to say different or it's incorrect. Because next time, maybe it'd be 15%, or the next time it might be 40%. It's one of those pendulum things where it just isn't settling in. That's the idea of a two-tailed test. So we can state that the difference between the 20% and the 22% is too large to be attributed to sampling error alone. So yeah, something's going on. Something's different about this survey. Okay, here's a mailing company that sells computer parts by mail, and it says at least 90% of all orders are mailed within 72 hours. That's just a number we don't need after they're received. So the quality control department of the company often takes samples to check if this claim is valid. And then a recently taken sample of 150 orders shows that 129 are done within 72 hours. So do you think that this company's claim is true? And strangely, they pick up 0.025 alpha. Now, they're saying that it would be within 72 hours. Well, they also said at least 90%, so it looks like this isn't going to be a one-tailed test. So we have the fact that we're interested in the less than, so we want to be at least 90%. So, so we've got to say that over here for a right tail test. And there's the bland equal sign that I always put in, but we have to make sure that things are up to what they're supposed to be. And looking at NQ for a moment, if N is 150 and Q is only 10%, which of course is the complement of 90%, we only get 15, so that's becoming kind of a close call, but even that makes it, and certainly 135 is greater for the NP calculation, so we're good to go. Z is ready to go, just like always. And so alpha 0.025, and maybe I got that backwards. I'm sorry. Yeah, it is a less than. I misread that. Sorry. That is a less than 0.90. Why do we know that? It said that the company said at least 90%. So yeah, this is one of those tougher kind of problems I do not plan to give you. I just plan to be more straightforward about it and not do that. So in a way, this is kind of like a greater than or equal to. That's what the company says. But it does say the dreaded word at least that a lot of students don't understand. But that equal sign is up in the HO, so you may say greater than or equal to if you want, but no obligation provided you get the less than part. But we're going to be more direct about it on the test. I will just say, is it less than 90%? That's the alternative, and that's how we'll say it. We're not going to try to fool you with those kind of subtleties. So it is a less than, and it's a left tail, and we're going to be looking at a negative value. And for this kind of thing, it just happens to be half of what we just did. We only have a negative here on the 1.96, and there is no right tail. And there's the picture. It's kind of like half of a 95% confidence interval. For the lowest 2.5%, that corresponds to a Z, still a very popular Z of minus 1.96. Now then the question is, do we go less than that to reject HO because it's strong enough, or we don't quite make it that far, or we can't reject it, then basically accepting or preferring the HO. Okay, here's some calculations. Sigma sub p hat, which does work out to be only 0.02449 or so. Then Z, test statistic, is calculated this way, and we do get, I always like to look at the numerator. There's a negative 0.04 up there, and that tells me what sign the Z will be, because your denominator is never negative, as you know. So we do get a negative 1.63, and it's greater than 1.96 negatives. Let's take a look at the picture. Minus 1.63 on a number line would be right about there. And it is greater. That's one way to look at it, but I look at it towards the center, towards the inner part of the curve. And yes, HO is our winner. Don't reject it. But I don't mind using contractions here. You don't have to spell out every single word. Okay, so yeah, that's not that strong a value. We're in the center, and HO is basically saying that we don't reject it, and we can say that the difference between the sample proportion and the hypothesized value of the population proportion is small. So not much happened here, and it probably happened just due to chance. Let's quickly review what HO said, because they're not really recovering what that was. And yes, we were saying that it was at least 90% or even just equal to 90%, and there was no evidence to say there was less than 90%. Not really. Notice, by the way, we kind of almost slipped this one past you. They did not directly give us 86%, but I believe 129 over 150 did work out to be 86%. That was 4% off from before, but not strong enough. Not strong enough. p-value would say the same thing. We're avoiding the use of p-value, but it would be relatively easy to look it up. Z is very friendly to the p-value. I'm just not choosing to emphasize that right now, but you may if you wish. Okay, so we already went through that one. Let's go to another part here. Z-test for the population proportion, and this is just kind of an instant review. Be sure we have the numbers greater than 5. Test statistic is the sample proportion p hat, and Z would be used assuming that these are in place, which they will be. So this is one way to look at it. Yeah, we'd have P minus mu of P and then sigma of P hat. I never use this formula, by the way. I just say P hat minus P divided by the square root of PQ over N. And there shouldn't be any hats down there, I don't believe. And verify that the sampling distribution of P hat can be approximated by the normal distribution. Yes, we just said that. And so we can go along that way. And let's continue. Page or part 2. State the claim mathematically and verbally. Please come up with your hypotheses. Specify they will specify the level of significance, that is alpha, of course. Determine the critical values. Use the table to do that. I'm going to use the critical value method here at least. Determine the rejection regions. You don't have to state that explicitly if you do a sketch. The sketch will make it obvious, which is why I like sketches so much. And find the standard test statistic and sketch the sampling distribution. So we have all of that going on. And we have the following as well. So check out one thing real quick here. Yep. Okay, so we have number 7. Make a decision. You got to make the call. And if Z is in the rejection region, you can reject HO. And that means you like HA, or H1. That's your favorite one. Otherwise, you fail to reject it, and you basically like HO. Not quite saying innocent, but you are saying not guilty. So that's the kind of the thing we go through. And then interpret the decision in the context of the original claim. So basically, you just look and see what your favorite hypothesis was, and you put it into words. Okay, here's an example. A researcher claims that less than 45% of U.S. adults use passwords that are less secure because complicated ones are too hard to remember. Well, they can be remembered. You just have to work at it. So, yeah, I've been locked out a few times. I think everybody has. In a random sample of 100 adults, 41%, which I imagine would be 41, say they use passwords that are less secure because complicated ones are too hard to remember. So at alpha equaling 0.01, is there enough evidence to support the researcher's claims? And notice they claim that less than 45% is happening here. And yes, we can use it because NP, which is 100 times 0.45, is 45. These are really easy calculations. 100 times 0.55 is 55, and yes, they're both greater than 5. So of course we can use a z-test, and it's nice to show that if you have time. The claim is less than 45% of the adults use the less secure passwords. So here are the hypotheses. And yes, remember to try to remember to put the decimals inside the hypotheses. So I'm just going to put down the one-size-fits-all equal sign on HO. And the claim, which is the alternative, H1 if you want, would be less than 0.45. And so many times the H1 is all you really need, but in a beginning class, we do have to encourage you to not forget about HO, even though it isn't quite as important. Sometimes we want you to write it down because typically there's a 1-point penalty when you don't put it down, unless you've done something else outstanding in your work. But, I don't count on that. So just go ahead and write down both hypotheses, please. So because the test is a left-tail test, and the level of significance is alpha equaling 0.01, critical value is z equals negative 2.33. The rejection region would be to be less than that particular kind of a strong negative value. So they calculate what z would be, and after all the calculations are done, 0.41 minus 0.45, a difference of about 4%, and then we'd have to, and they really dropped the ball on this one. They lost a lot of stuff out of this. But there's your Q, there's your P, PQ divided by N, all square rooted. We get a very moderate value of 0.80. Wow. Here's kind of a little topic I'd like to mention. Anytime you have a 0 in either your t or your z, H0 is your winner. I don't think that's a coincidence, but if you got a 0 and what you've tested from your data, I like to call this Z data, by the way. That's just the way I learned it. Z critical value, Z data, that way you can tell what they are. And if you get a 0 in either Z or T, H0 is your winner because it's really in the center. This is a center kind of a deal. And that's what HO loves. It loves the status quo close to the mean as possible. But here's the picture. Lovely picture here. We have the location of the rejection region, minus 2.33, and how we weren't even close. We actually like HO here because it's really close to the center. That 4% difference here isn't very much. Who knew? Sometimes it is and sometimes it isn't. Z is not in the rejection region. You do not want to reject the null hypothesis. In fact, you kind of like it. You like HO because this is very moderate. This is very centered. And that's not going to support going left or right or even to a two-tail scenario for an alternative hypothesis. And there's not enough evidence, especially at the 1% level. That's really a hard bar to cross anyway, of significance to support the claim that less than 45% of adults use the less secure passwords. Okay, now we've kind of gone through this already. I didn't really show the example, but sometimes they may not give you p hats. You may have to get that yourself. And this is right out of the binomial part of the class. And x is the number of successes, and n is the sample size. Of course, it's little n. And in this particular case, a researcher claims that 51% of U.S. adults believe incorrectly that antibiotics are effective against viruses. Yep, there's viruses, all right. And then the random sample of 2,202 adults, that's pretty large, and 1,161 say antibiotics are effective against viruses, so they're wrong. And at alpha equaling 0.10, rather loose standard, but that's okay. We don't worry about that. Is there enough evidence to support the researchers' claim that 51%, and notice no direction, so that's equals 51%, and then the other one will have to be not equal to. No direction hit. There's no greater than, there's no less than. Look carefully for that. And so we double check to make sure we're all doing everything okay. So this is always a good idea. Yeah, 1,123 looks pretty big. And then Q, you multiply it and you still get over 1,000. They're both greater than 5, so of course you can use a z-test. No problem. And the claim, 51% of the adults feel that antibiotics are effective against viruses. So going to decimal form, calculator friendly, so HO colon, P equals 0.51. And we had that different from 0.51, so this is the two-tail test. So just simply put a not equal to sign there. And it's a two-tail test. Level of significance was 0.10, that's alpha. And critical values happen to be minus 1.645 and positive 1.645. This is very much like a 90% CI. Same exact numbers, except now CI is in the middle, and what we're looking at is the tails. So they're two different things. They both have the same Z values. There's a negative, there's a plus. And the plus is optional. I'll put the dots in though, make sure the decimal's in there. Okay, so now we have this kind of a thing, and they've gone ahead and found what the proportion will be, and they probably rounded this to 3 decimals, which I would say is all right. So 0.527, and that's what we have, and that was compared to 51%. So let's go ahead and show a little bit more information that they strangely delete from this. And then we have to figure out what P and Q are. So that would be 0.51 times 0.49 over 2202. And that's, I'm not sure what the 1 is. I'll just cross that out. And, oh yeah, it was 1.60. That's what it was. Okay, so that's a little bit hard to follow, but 1.60, rather moderate value of Z. And look how close a call that was. Wow, that was close. I used to put problems like this on my finals. And I guess I could dust off some ideas and bring it back, perhaps. But this one is really close. We were trying to get over the hump of 1.645, at least on the positive end of the scale. And we got close, but not quite. We're still where HO lives. We fail to reject the null hypothesis. It's just not quite big enough. That dot is right on the line almost, but not quite. So there's not enough evidence at the 10% level, the loosest level of significance, to reject the claim that 51% of the adults believe incorrectly that antibiotics are effective. So we're not going to reject it. We are saying that, yeah, it sure looks like close to 51% to me. They just don't like to say it quite that way, which is quite confusing to many students, but depends on how you think. If you think, especially if you think like a lawyer, you shouldn't have any trouble at all with this, but just kind of push it together, and that's another reason why I say if you just want to prefer hypothesis, just give me the evidence, and I don't care how you write it up so much. That's the end of the slideshow. So what we have left now is Chapter 10. So Lecture 17 and Lecture 18 have yet to be had. Lecture 17 we'll do 10.1 and 10.3. And Lecture 18 we'll do 10.5 along with a review for the final. So we're going to work out something for the final that avoids so much downloading, and we're going to see how that works out. But we're going to put something together here pretty soon, so we'll be coming out probably a little bit earlier than normal with the next couple of lectures, but remember, we try to adhere to the Tuesday, Thursday schedule, even if we come out a day early. Certainly don't plan to be late from here on in. In fact, we'll have a quiz that just barely gets in under the wire for some of you on the final, so yeah, we'll have a kind of a special email for some of you in that one particular class that has that issue. We'll want you to, if you well, there'll be a kind of an issue that we'll get to later, but some of you that are taking the early final may want to get done with the quiz just a little bit earlier than the deadline. It would be to your benefit to do that. That's all I'm going to say about that right now, and we'll have more to say about that later, and we'll try to cover a few typical problems in Lecture 18. But we still have Chapter 10 to go. It's really an extension of Chapter 9. It's just more hypothesis testing. The only difference is we have two sampling proportions to deal with, or two sampling sets of data, such as males versus females, or Easterners versus Westerners, or Canadians versus Mexicans. Any two groups you can think of that have some kind of characteristic that might be different in some direction, we can test it. And it focuses on two different populations, and we'll explore that in three different sections. And that's all we have left in the class. We're getting close to the end. I encourage you to try the office hours. Make sure your Zoom works, because if it doesn't, that's not going to be too good for your final. Basically, you fail the final. So be sure you've tested your Zoom. Almost all of you were fine with it. I will ask you point your cameras towards your face a little bit better. No light sources in the back. If I can't see your face, I'm going to let you know about it, and I'll give you a warning, and that's going to be all you get is a warning, and then I'm afraid I just won't be able to use your results. So a lot of you were like pointing right at a light bulb or something, so I couldn't even see who you were or anything, and that's not going to be acceptable this time. I don't have to see every single expression, but if I really can't even see your face at all, I'm going to let you know, and maybe I'll have to use all caps, but not that I want to, I don't. But we do have to have the Zoom record what you're doing. So anyway, enough of that. Study hard and seek out the office hour. I'm willing to help you out, and we'll talk to you later.